tonight, 2.10 to 2.14. 2.14 is a little wrong. It's the carbonyl section. It's pretty long. I will get your homework posted sometime soon. Today or tomorrow morning. I haven't started it, I'll admit, and so it's going to take me a little while to collect all the spectra stuff. Alright. So, we are going to start out talking about these bond vibrations we've talked about with the IR spectra and infrared wavelengths of light. There's one thing I want to specify with all of our energies. When we're talking about molecules, we are talking about quantized energy that they can absorb. A molecule cannot absorb every single type of energy. It only can absorb specific energies that correlate with differences in energy levels. So there's a couple different diagrams up there. But we are looking at the quantized energy. And that corresponds to the difference in energy between two energy levels of the molecule.
Thank you.
And every bond is going to have a different set of energy levels. We're talking about vibrations here, so we're talking about the energy of vibration of a bond, and each one is going to have a slightly different set, which is going to have a different energy difference. So if we look at this simple harmonic oscillator, this is how we would look at a spring with two balls on the end. And if you gave that ball with the spring in the middle a little bit of energy, it's going to start vibrating. If it's a simple spring and two balls, you can give it any amount of energy and it's going to take whatever energy you get and vibrate at that energy level. For the bonds, we're going to have specific energy levels that they are going to correspond with. I got that from the internet. I think it's 12. I'm pretty sure that 2 comes before 3.
Are you sure?
Yes. It is quantum mechanics, so it could be crazy, but I'm pretty sure 2 comes before 3. So B equal to 0 is going to be our ground energy level. This is your standard vibration of an energy, or of a bond. Bonds are not static. They do have a slight vibration at their lowest energy level. And when we shine light on it, if that light corresponds directly to this difference in energy between the V equals to 0 and the next highest energy state, so we have a difference in energy of whatever that measures out to. If we get a wavelength of light that's exactly equal to that difference in energy, you're going to get excitation of the bond energy to its next highest vibration state. And in here, the axis is energy versus bond length. And the R sub 0 is going to be our standard bond length. And there is going to be a little bit of compression of that bond length and a bit of extension when it's vibrating. And so R sub 0 would kind of be the average of the two. And then our E, is it EQM on it? Yeah. Is going to be your average bond length again, right there in the middle. And you have that vibrating a little bit, so it's a little shorter, and then a little bit longer in the 0 or 1. Note that you go out a little bit further as you get to a higher energy state. This would be the exact model we would use for a ball and spring again, but we don't have a ball and a spring. We have two atoms and a bond between them. You cannot go to infinite distance between the two atoms in the vibration, or else you're going to end up breaking the bond. And so the actual aharmonic oscillator that we're going to use as a model is the compression side stays essentially the same. There's only so close they can get together before they would be colliding with each other in the bond length. But if we get to high enough energy in that bond vibration, we're going to dissociate the two atoms. Notice that this is quite the energy difference between all of those, so we'd have to get up to a very excited energy. It's hard to do that, and that would be a different kind of wavelength of light that's going to do that. Okay?
Sorry, is it aharmonic or anharmonic?
Anharmonic.
Okay.
I keep forgetting the N. So it's an anharmonic oscillator. There is a website called Kim 3D Tube, which has some animations. So if we look at this one, we have carbon dioxide. This slows down the computer a bit, but here is the carbon dioxide vibrating at the 0 energy level. If we were to give it a little bit more energy, if I select on the P equals to 1, you'll see that it starts vibrating a little bit faster, a little bit more excited energy state. And that is for one of the vibrations. There are a bunch of different ones here. So we can have stretching and bending, which we'll get to on the next slide. Water wasn't working for me earlier. Let's see if it's working. But the HCl is really obvious with the different energy levels, so you can see a slight vibration there. If you give it a little bit more energy, that hydrogen is getting more excited and going further out. If we were to go up to the second energy level up, you're going to get much higher faster stretching and further out, and then even higher energy levels. But again, we're not going to be looking at those highest energy levels most of the time. We'll just be looking at the bottom one. A reminder, is there a question?
Yeah. I was wondering, is REXP different than REQM?
So in this one, this is again going to be our average bond length. But note, because we have the anharmonic oscillator, that it's not quite the same. So here, our average bond length is right at the middle. Here, because our difference between our compression and extension as we go up in energy is getting greater and greater, our experimental average bond length is getting further out. And so it's the same, but for a real atom. As a reminder, we're only going to see these absorptions when we have dipole moments. So our IR active bonds are the ones with dipole moments. then we may refer to things as IR inactive bonds, which have no dipole moment. Most specifically, the ones we're going to be looking at that we might not see would be your triple bond carbon with two carbons on either side of it, or a double bond carbon, again, that's very symmetrical. You know, when we talk about organic molecules, we essentially say they are nonpolar because carbon and hydrogen don't have a dipole, but they have a little dipole, and we can measure that with IR, and that's why we see the CH bond stretches. Any other questions? This was from the IR tutor, and so if you have a higher frequency, you're going to have a larger spacing between your energies, and that's going to show up at the higher frequency here. As the energy difference between those goes down, if we have the energy difference being closer together, then the frequency is going to be lower. So for energy, we have a high energy, we're going to have a high wave number. And as the energy goes down, so does the frequency. And you can see they get even closer together, and then you get even lower frequency. Now we get to do our aerobic exercise for the day. Okay, so we're going to look at some different terms for stretching and bending. And you all get to do this with me. Yes. I feel like a fool. We can all feel like fools together. So we have asymmetrical stretch. It takes both of your hydrogens out here, and they're going to stretch together at the same time, right? So that would be asymmetrical stretch. Now, asymmetrical stretch is going to have one end.
That's true, but still.
Alright, a little explanation on the other ones. These are going to be bending ones. So instead of stretching, we're going to start out here, scissoring, kind of like it sounds like, scissoring your arms back and forth. Your rocking is going to rock side to side. And then wagging. Can't go very far backwards. And then twisting. One's going forward, one's going
Using bow sticks tracks.
those are going to be, so we will refer to our stretches as symmetric or asymmetric, and then our bends as scissoring, wagging, rocking, or twisting. We may not distinguish all of them, but some of them we will talk about. Notice the relative amplitude of those, or the frequency. So our stretches are going to have higher frequencies on average than your bends. These are all CHs, and so the CH stretches tend to be between 2800 and 3000, higher energy. The bends are going to be lower energy, each of these varying from 1400 and 1200, 1200, and 700. So lower energy for bending. And this is stolen directly from your textbook for those pictures. You want to recreate each of those. Okay, that's pretty much all I understand that. But the next slide has a bunch of words on it, and that's all. So I might just leave this up and I'll write out all the definitions on the board. Okay, we're going to start with the fundamental absorption. These are the ones that you learned in organic chemistry. Your fundamental absorption is going to be the excitation from the ground state energy level to the first excited state. And that's the one that we were talking about on this slide. If we were looking at our anharmonic isolator, that's going to be the difference between B equals to 0 and B equals to 1. That is going to be your most common absorption, and the one we tend to interpret the most. But there are going to be additional peaks in our spectra that we have to interpret that are not coming from these fundamental absorbances. I think your old textbook, if you took organic here, talks about the maximum number of fundamental absorbances is going to be dependent on if it's a linear molecule. If it's linear, it's 3n minus 5, where n is equal to the number of atoms. So if you were to have 3 atoms in your, well, let's say 2 atoms in it, you're going to have 3 times 2 is going to be 6 minus 5. You'd have 1 stretching, because you just have 2. So it can only stretch in one way. Yeah.
And this is max number of maximum fundamental peaks, or I'm confused, what is the fundamental?
The fundamental absorptions where you have that energy level delta 0, or B is equal to 0 to B is equal to 1.
So
To the first excited state.
So it's saying like the max height?
No, it's just if it was the perfect spectrum that only had excitation from a ground state to the first excited state, this is how many you would see. We're going to see more than that though, because molecules are more complex than that. If it's a nonlinear system, 3n minus 6. Somewhat useful for your smaller molecules. You're going to have something, say you had 4 atoms, then you would have 3 times n would be 12 minus 6, you're going to have 6 stretching frequencies. As we get up to, say, benzene, 12 atoms. 3 times 12 is 36 minus 6, 30 fundamental absorbances for benzene. So it gets pretty complex, and you're not going to be able to identify all of those. I say maximum number because sometimes they're identical. So looking at benzene, it has C double bond stretches all around, and CH stretches, they're all equivalent, and so they don't all show up because they can show up at the same place. And so we get different things like that. We also are going to see some other types of bands. The fundamental are kind of your easiest to understand. The next ones, we're going to go to the overtone. excited to not the first energy state, but one of the higher energy states. So if we look at this graph here, we're looking at a difference in energy from your ground state up to, say, V equals to 2. Mathematically, it tends to be that this is either going to be 2 times your fundamental frequency or 3 times your fundamental frequency. So let's say we're looking at a C double bond O. This is the one you're going to see it for most commonly. If that had a stretching frequency of 1715 for your wave numbers, you may see an overtone at 2 times 1715, which would be 3430. What region would that be in for our standard, if we were just looking at a spectrum, what would we might think that was? What might we think that is?
Amine.
Alcohol, NaOH. People sometimes see this overtone peak and start thinking that there's an NH in there, since NHs don't show up very well. But it is actually the overtone of the C double bond O. Turns out that these are actually quantum mechanically forbidden, and so it doesn't happen very frequently, but you do see the peak in there, especially for strong frequencies. Still happen for a strong fundamental. We're going to see some overtone. We need to be able to recognize those. But remember that it is 2 or 3 times the stretching frequency, and so if you see a really strong peak, it's good practice to double that peak and see if there's another smaller peak in that region. We'll see some examples of those as we go through the different functional groups next time. Okay, so the overtones is a multiplication. The next two are addition and subtraction. So you may see a combination band. Where 2 vibration frequencies couple. In this one, let's see, we have vibration frequency 1 adds to vibration frequency of 2, and then we get the combined vibration frequency between the two of them. We'll examine those as we come to different functional groups that may have those in them, and your book specifies them. The other one is the difference band. In this one, so in the combination band,